Hello, Dr. J here. In this short tutorial, we're going to look a little bit more detail in the transformer. So here we have a diagram of a transformer. We have on this side the primary coil and the secondary coil. This is an iron core which increases the power efficiency between the primary and the secondary through a changing magnetic field. So here on the primary side, we have a primary winding, as I mentioned before, with the number of turns equal to NP. On the right side is our secondary winding with a corresponding number of turns of NS. We have a plus and minus voltage applied at the primary, and we denoted that as the primary voltage. And on the right side, we also have a corresponding secondary voltage denoted as Vs. In addition, we have the current, IP, known as the primary current. And on the output side, or the secondary side, we have the secondary current. Now let's look at a schematic of a transformer. Here we have a schematic of a air core transformer because there's a gap between these primaries with nothing in between, whereas an iron core transformer is represented by these two vertical lines. We also have a center tap iron core transformer where we can have two basically outputs for this type of transformer, but our primary concern is either the air core transformer and the iron core transformer. So we're going to look at efficient power transfer. On the primary side, we have our well-known formula, the power formula, where P is equal to IV, where the subscript P stands for the primary. And on the secondary side, we have the same type of formula. The power output at the secondary is equal to I sub S times V sub S. Now, the transformer is a passive device, so it does not require power to make it work. It just requires that we have the iron core to have an efficient power transfer from the primary side to the secondary side. With efficient power transfer between the primary and secondary side, then very little heat is dissipated on the transformer. In other words, we have P sub P equal to the secondary power. And substituting in for the IV relationships, we have the primary current times the primary voltage is equal to the secondary current times the secondary voltage. This is useful why the high voltage in your power lines is high, because in order to keep the power constant, the current has to be smaller in order for this relationship to hold. And when you have a smaller current, there are smaller losses due to the dissipation of heat as the power gets distributed from the utilities to your home.